Let's take a look at how to solve a classic conservation of momentum problem. In this case, it's a watermelon explosion, but it's not going to be that interesting because it's simply going to be involving Biff throwing a watermelon. So typically when we have two objects, it could be many objects, but we're just going to deal with two objects and they are together and not moving, and then they push off and they go in opposite directions, we're going to call that an explosion. So this is not really an exploding watermelon in the exciting sense. It just involves Biff is holding onto a watermelon. He pushes on the watermelon. It pushes back. They separate and go off in their respective directions. Now, what ultimately is the question I want to answer using conservation of momentum? And that is, what is Biff's speed after the throw? So we know going in that that the initial velocity of both Biff and the watermelon is 0. We also know that there's no information about force. There's no information about impulse. So we cannot use Newton's second law. We cannot use the impulse momentum theorem. So we can use conservation of momentum if we can find that the requirements for conservation of momentum are satisfied. And what we have to do is, let's think about what an appropriate system would be. Now, Biff's momentum is going to change because he's going to go from not moving to moving to the left. And the momentum of the watermelon is going to change because it's not moving initially and it's going to be moving. So neither Biff alone or the watermelon alone would be a good choice for a system, because in neither of those systems would momentum be conserved. However, if I think about the Biff watermelon system as a whole, I can say that the momentum of the Biff watermelon system will be conserved so long as I can say that the net external force is 0. So basically what we have is we have gravity pulling down on Biff. Biff is actually holding up the watermelon. Don't worry about that though, because he's holding up. So you can think of the gravity is pulling down on Biff and the watermelon together, but the force of the floor upward is completely matching gravity. So in this case, we can say that the net external force is 0. So since all of the outside forces, gravity down and normal force up, equals 0, we can say, let's see, I don't want to lose my picture too much, but I'll come back to it. We can say that the momentum of my Biff watermelon system before the throw is going to be the same as the momentum of my Biff watermelon system after the throw. Recall that prime, this little prime here, means after. Okay, so where do we go from here? We know momentum is going to be conserved, but how do I get the answer? And this is, I would suggest you follow this format for all problems. There will be some variation when we get to another type of problem, which would be a collision problem. But in general, I would follow this basic approach. We're going to say that the momentum of, now I'm going to write m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And this, I would write this down, or at least think this step for every single two-body conservation of momentum problem. In other words, if you've got two objects, start with this. All right, now, who's 1 and who's 2? I don't try to get fancy naming them. So I'm just going to say, Biff, you're number 1. And that means, there's a lot of red here. That means, hey, watermelon, you're number 2. So Biff is number 1 and the watermelon is number 2. Because does it really matter that it's Biff and a watermelon? No, this could be any two objects in the universe. So I don't get fancy with the naming. Now, this is what I'm highlighting right here is basically my starting point for all problems. And now the next step is to say, okay, what's going on in this particular situation? Well, let me step back one bit, because where's the answer here? In this equation that we're looking at right here, what is the answer and what am I looking for? And it is Biff's speed after the throw, and he's number 1. And so this is what I'm after. This is the answer, right? I mean, that's if I can solve for V1 prime, that's my answer. Okay, now the next step is, okay, customize this kind of starting point for our particular problem. And by that I mean is, let's look at what Biff and the watermelon are doing before the collision, and the answer, before the explosion rather, and the answer is nothing. So that means Biff isn't moving and the watermelon isn't moving relative to some local frame of reference. And so that means that there is no momentum in our Biff watermelon system before the push. Well, guess what? That means after the collision, sorry, I keep saying collision, after the explosion, the momentum is still going to be 0. Okay, so that means I can set the left side of the equation, which is 0, equal to the right side. Let me get rid of that arrow, but that is what we're after. All right, so now let's just bring down m1 v1 prime plus m2 v2 prime, and I'll go ahead and say, okay, that's what we're after. So now I'll say this, basically the physics is done, and it's just a little bit of math to clean up to get the result, because what I want to do is I want to rearrange to solve for v1 prime. And it turns out I know the mass of Biff, I know the mass of the watermelon. Oh, that doesn't belong there. Sorry, the 2 goes on the bottom. That's not squared at all. Sorry about that. So that is just v2 prime. All right, so now I'm just going to basically solve for v1 prime. I basically push, well, just let me try here. So basically it's going to be negative m2 v2 prime all over m1. And how I usually write that is v1 prime equals, and I put the negative sign. That just tells me the watermelon's going one way and Biff's going to go the other. And then there's this ratio of the masses. And then there's this velocity of the watermelon prime. Let's plug some numbers in there. Again, the negative sign just means, hey, Biff is going left when the watermelon goes right. Okay, their masses, Biff is 50 kilograms, the watermelon is 5 kilograms. So we've got, oh wait, no, this is the watermelon here, 5 kilograms over 50 kilograms. Now, does that make sense? I think so, because that means Biff is going to be going much, much slower than the watermelon. And hopefully that makes sense, because he's got a whole lot more mass. What's going to be equal and opposite are their two momenta, the momentums of the two, not the velocities, because they have very different mass. Okay, now how fast is that watermelon going? 20 meters per second. Pretty good throw, Biff. Okay, so basically I've got negative 5 divided by 50 is 0.1 times 20 is 2 meters per second. So Biff is going to go to the left at 2 meters per second when the watermelon goes to the right at 2 meters per second. So this is just basically how you approach conservation of momentum problems. In another example, we'll do kind of a collision. In that case, there are a couple of little subtleties, but not that much different. Okay, bye.